In this video, we'll be talking about all the events associated with blood flow through the heart in one complete heartbeat, the cardiac cycle. Just a couple of quick definitions before we begin. First, systole. Systole is contraction of the heart muscle. So when you see systole or systolic, think contraction. Diastole is relaxation. So when you see the term diastole or diastolic, think relaxation of the heart muscle. In a single heartbeat, you have to consider both the atria and the ventricles. So you have atrial systole and you have atrial diastole, but you also have ventricular systole and ventricular diastole. Note that these overlap. The atria contract while the ventricles are relaxed, and the ventricles contract while the atria are relaxed. It's a continuous cycle, so it's a bit arbitrary as to where you set time 0 for a single heartbeat. But here, we're looking at time 0 as the beginning of atrial systole. Note that ventricular systole does not begin until the atria are done contracting. Now let's bring the heart into our picture. Here we can see what's happening to the heart throughout the cardiac cycle. First, we have atrial systole. The atria contract, squeeze down to force the last bit of blood down into the ventricles. Both the right and left atria contract at the same time. Next, in B and C, you have the atria relaxing and the ventricles beginning to contract. Both ventricles contract simultaneously. Remember that the AV valves close when the ventricles begin to contract, so blood does not get pushed back into the relaxed atria. The first phase of ventricular systole is called the isovolumetric phase. The ventricles are contracting, but they haven't quite created enough pressure yet to open the semilunar valves and eject blood into the arteries. So since nothing's ejecting, there's a steady amount of volume, of blood volume in the ventricles, and that's why you get iso, which means equal, volumetric contraction phase. The second phase of ventricular systole is the ejection phase. In this phase, pressure in the ventricles is high enough to force the semilunar valves open and eject blood into the pulmonary trunk and the aorta. As ventricular diastole begins, the relaxation phase, the semilunar valves close as blood falls back against them. The AV valves open a little bit later in the phase, and blood drains into the atria from the veins and down into the ventricles through the AV valves. This is a slightly different view of the cardiac cycle. It starts at a different point in time, which of course doesn't matter because we're talking about a cycle, so like I said, it's arbitrary as to where you set time 0. I'm showing this diagram to you because I like how it illustrates the different phases in ventricular systole and diastole. So, starting at the beginning here, we have late ventricular diastole. Blood is passively draining from the atria into the ventricles. About 80% of blood enters the ventricles this way. The last little bit, the last 20%, happens during atrial systole, when the atria contract and force that blood down. After the atria relax, the ventricles start to contract. There is a really brief, that isovolumetric contraction phase that lasts just for a moment before the semilunar valves open and blood is ejected into the aorta and the pulmonary trunk. After the ventricles relax, there's a momentary phase when the AV valves are still closed, before the pressure of blood accumulating in the atria forces them open. Then we're back to the passive ventricular filling phase again. So this wraps around. back to passive ventricular filling. This diagram shows how the mechanical events of the cardiac cycle match up to the electrical events shown on an electrocardiogram. Remember that the P wave is atrial depolarization. Notice how atrial systole follows pretty much on the heels of that P wave, just slightly after. It's the depolarization that the P wave represents that stimulates, that triggers contraction of the atria. Then you have the QRS complex, ventricular depolarization, which stimulates contraction of the ventricles. Ventricular systole starts in about the middle of the QRS complex. The T wave represents repolarization of the ventricles, which allows the ventricles to relax. So the T wave putting the ventricles into ventricular diastole. If you can work through this graph and understand what it's showing, you will understand the events of the cardiac cycle. This graph just shows everything that's happening in the heart during a single heartbeat, a single cardiac cycle. Time is on the x-axis, so you can pick a single point in time and look up the graph to see everything that's happening at that moment. Let's pick it apart now and see what it shows. At the top here, you have the electrical events on an EKG. We already talked a bit about how the EKG relates to the mechanical events in the heart, so let's set this bit aside for now. On the bottom here, we have left ventricular volume. You see passive filling up to this point labeled 1, then atrial ejection up to 3. Okay, so notice how there's a little bit of blood, but then there's just that last little bit getting squeezed in when the atria contract. This takes us to the point of maximum blood volume in the left ventricle, called the end diastolic volume, or we'll be referring to it as EDV. Between the end diastolic volume and point 6 down here, we have ventricular contraction, ventricular systole. This is when blood is being ejected out to the aorta. There is still a small amount of blood left in the ventricles at the end of ventricular systole. This is your end systolic volume. Once the ventricles relax, passive filling begins again, and you start seeing the blood volume in the left ventricle going up. Now let's take a look at the pressure graph. We'll start with the left atrium. That's the line in blue here. With the left atrium, you see just a little rise in pressure as the atria contract. See how this corresponds to the active filling phase in the left ventricle? There's not much going on with this line. There's just a little bit of a blip in pressure when the left AV valve closes and when the left AV valve opens again. Now let's take a look at pressure in the left ventricle. This one's a little more interesting. In the left ventricle, remember we're looking at pressure now. So you have a little blip as the atria contract and blood is being pushed down into the left ventricle. But when you really see pressure rising in the left ventricle is when ventricular systole begins. That's what's happening with this big mountain. See how that corresponds to ventricular systole up here? And see how it corresponds to the drop in blood volume as blood is ejected out to the aorta. Pressure falls as the ventricles relax. Last line on this pressure graph is the aorta, and that's in black. In the aorta, you see a slight decrease in pressure until the ventricles start to contract. At that point, blood is being ejected into the aorta, and you see a rise in aortic blood pressure. It's kind of disappearing behind the ventricle line here. It starts to come back down again as the ventricles relax. There's a little blip in aortic blood pressure here. It's called the dicrotic notch. what happens is that the aorta is a very elastic, thick-walled artery. So those elastic walls get stretched as blood is ejected into the aorta, and then they snap back a little bit as the ventricles relax. So this little blip, this little rise in blood pressure is from the elastic walls of the aorta recoiling back and causing just a blip of an increase in pressure. So this is a complicated graph. There's a lot going on here, but if you break it down, take it piece by piece, and see how those pieces relate to each other, it's not nearly so intimidating. After studying this video, you should be able to distinguish between the different forms of systole and diastole. You should be able to explain what's happening in the heart during the cardiac cycle and relate these events to blood flow through the heart, the electrical activity of the heart, by which I mean the EKG, and pressure changes in both hearts, atria and ventricles, and the aorta.